Okay, so buoyancy. So imagine that we have an object and we hook it up to a spring scale and we hold it up in the air. So there's a force of gravity acting on that object, and the object is supported by the spring scale, and so those two forces are balanced. Now if we lower that object into the water, well, the force of gravity is the same, it's still the same object, but you'll see when you do that that the apparent weight of the object, which is the scale reading, gets a lot smaller. The reason for that is the water actually pushes up on the object, and that's a force that we call buoyancy. So if you draw this carefully, so this arrow and this arrow are the same length because those forces are balanced. This arrow is the same length because it's the same weight of the object. And these two arrows should add up to be the same length as this one. So what is this force of buoyancy and where does it come from? Well, it turns out that this relates to an idea from last class. You see, if we look at the pressure forces on an object, the fluid will push in all directions on the object, and the left and right ones cancel, but the up and down don't cancel. The reason for that is the pressure and force on the bottom is a tiny little bit bigger. Why? Well, because pressure increases with depth. So the pressure on the bottom is always going to be more than the pressure on the top. Now the relationship that we had for that last class was this one here. It says the pressure at depth is due to the air pressure or weight of the air column plus the weight of the liquid that's above you. So because pressure increases with depth, the upwards force, the pressure force on the bottom, is always going to be bigger than the pressure force on the top. So the net of those two is going to be upwards, and the net of those two is what we call buoyancy. So I'm just pausing for a sec for you to finish writing that down. Then we're going to move on and do an example. On page 35, we'll do example 5 together. All right, so I'm going to change the slide now. So here's example 5. So we have a bundle of plywood that is floating in seawater. So the only forces acting on it are weight and the upwards push from the water that we call buoyancy. Now we're asked to write out relevant physics equations. The first relevant equation just comes from physics 11, and it says that if that object is at rest, and it is because it's just floating in the sea, then the forces have to be balanced. Now that equation is true, but not immediately useful because we don't know the mass of the plywood. You'll see later we can find it, but it's not given information. So let's consider the next relevant equation, which comes from the Archimedean principle. The force of buoyancy depends on the density of the displaced fluid, the Earth's gravitational field, and the volume of the displacement, or the volume of the block that's submerged. Now, what is the displaced fluid? Well, actually, hold on. Let me annotate that equation a little bit. So rho in this equation is the displaced fluid. V in this equation is the volume of the block that's actually submerged. So let's annotate the equation a little bit, because we know the displaced fluid in this case is seawater. Now, how much is submerged? Well, we're given some dimensions. We know this bundle of plywood is 3 by 3 by 2 meters, but not all of it is submerged. Only the distance d is submerged, so it's less than 2. So submerged will be the base area, 3 times 3 times that submerged depth, d. So whatever d is, the buoyant force will be 3 times 3, which is 9. 9d times g times the density of seawater. Okay, so that equation comes to us just from the theory of buoyancy, from the Archimedean principle. Finally, from like Science 9 or 8, we have the definition of density. We are dealing with the density of the wood block here, so the object density is its mass over its volume, and then in this equation, that volume means the volume of the whole object. So the whole object was 3 by 3 by 2 cubic meters, right? So that's 18 cubic meters. And so now, because we know the density of wood, you can see that, aha, we can find the mass. So the first step would be to find the mass. Once we've got that, then we can find the force of buoyancy using the first equation. We know it's just mg. And then we'll use our buoyancy equation to figure out what d is. Now, we weren't actually asked to come up with a number for it, we were just simply asked to come up with a strategy. So, in solving the buoyancy problems that we're going to look at today, I mean, sometimes you'll only need one of those three equations, or sometimes you'll need all three, or some combination of two, or what have you. But the relevant physics principles are simply, well, draw a force diagram, and then say forces are balanced. Write an Archimedes equation, rho GV, but think carefully about which density and which volume to use. And then finally, reach back into your elementary science knowledge and write out an equation for density. So I've done 5. Now I'd like you to turn to the next page and try example 6. And try that now. All right, so you've had a moment or two there. Let's start just with the force diagram. Just make sure we're on the right track there. Obviously, the Earth pulls down on the block of foam. Strings can only pull, they can't push, so the rope is going to be pulling down. And finally, buoyancy is always upwards, so there's an upwards force of buoyancy here. Whoops. So that's the force diagram. Right. So I suppose you could proceed then directly to the first equation. So balanced forces just tells you that tension plus the weight must equal buoyant force. And I suppose if you wanted to substitute in, you could put in the mass, because we know the mass is 25 kilograms. So tension plus 25G equals buoyant force. Okay, so there's your force equation. I'll give you another minute or two to write a fluid equation and a density equation. All right, let's compare notes then. So for the next equation, we know that the force of buoyancy is rho GV. Rho is the displaced fluid, which in this case is water, fresh water. And V is the displacement, which is the amount that's submerged. Well, the whole thing's submerged here, so V is just V. And now if we substitute in what we know, we put in the density of 1,000, and there's still two unknowns in that equation, buoyancy and volume of the object. So we are going to need a third relationship, which is the density of the foam. Density is mass over volume, and it's the whole object. Now, we know the density of the foam is given as 300. We know the mass is 25. So there you go. Aha, we can actually solve this equation for something. So those are the three equations. And if you're like more concrete things with numbers, then they're over here. Now you should feel free at any time we're going through this, you want to just take out your phone and take a picture of the slide, and then you can write it out later. That's a good strategy if you're, behind for some reason. So what we need now is a strategy for finding the unknown. We were asked to find tension. And once again, we're just going to solve this one first. So find the volume. Find volume. Then when you got volume, put it in here and calculate buoyancy. And when you got buoyancy, put it in there and find tension. So that's our problem-solving approach. So that problem sort of scaffolded for you. It's structured a little bit. And you should now be ready to tackle today's list of problems. So today's list is at the end of the notes package. And so what we're going to do is we'll spend about an hour working on today's list. And I've got some helpful slides. So, as always, you work on it for a bit, and then we'll talk about it, and maybe I'll give you some hints. And then we're going to come back, and there's one more example we're going to do together, which is the iceberg problem. And so we'll get to that, in about an hour. So the objective in this sort of approach is that we mostly get the homework questions done here together, and then you can go away and work on the assignment. Now, assignment 2, you still have a little bit more than a week. Sorry, assignment 1, you still have a bit more than a week to finish it, but you should get to it because there are definitely some tricks to it. And there's been lots of students emailing me and asking me questions, so that's great. Everybody, though, should get started on that. So what are the assigned problems for today? I'll switch the slide. Here are your 5 for today. So it's page 42, and it's 3, 5, 9, 10, 14. So let's turn our attention to those, please. And I'm going to mute my mic for a bit. But I'll be right here, and I'll come in and talk about question 3 in just a few minutes. All right, so number 3 comes down to a bit of reading comprehension. We have to attack sort of the words that are written there. So we try and imagine what happens. Here we've got a nice slide here showing that. So here they are pulling up the anchor. And so the anchor has weight, and it's supported by the seawater, and then there's tension, and that's the force that they're pulling with. And what we're told is that once it leaves the water, it feels 200 newtons heavier. Now, it isn't really heavier. Mg is the same as it was. When we say it feels heavier, that means they have to pull with 200 more than they were before. So if you compare those two, there's a conclusion to be drawn there. What is that information really implying? Well, this is a lot like the place where we started class, where we lowered the bowling ball down into the water, and then it was easier. It felt lighter. The reason it felt lighter, of course, is that the water was pushing up on it. This slide should be helpful for you. I'm not going to give it away right away, though. I'm going to let you ponder this diagram and draw your conclusion from that. Okay, so no one's chimed in with anything yet. What conclusion do we draw from this slide, please? Yes, there we are, indeed. So if it gets 200 newtons heavier when you lift it out of water, that's because buoyancy was 200 newtons when it was in the water. And so with that information, it should be possible, knowing the buoyant force, it should be possible to find the volume. And so this is how you do it. You use the buoyancy equation, rho GV. That was just a quick look. I'll put that up later after you've had some time to work on it.
Professor Mathewson?
Yes.
Cameron again.
Hello, Cameron.
Yep. So we would then have to use water density in this case. Why do we need to use water density?
Well, because in the buoyancy equation, when we write buoyant force is rho GV, this rho is the density of the displaced fluid. And they're on a river, so it's fresh water.
Right.
It's 1,000.
Okay, thank you.
Yep. So with this equation, we need to know what the rho means and what the V means. The rho always means the density of the displaced fluid. And the V here is the displacement, the amount of the object that's submerged in the liquid.
Okay, thank you very much.
Yep, my pleasure.
Hi, Don.
Yes, hello. Who's speaking?
Hello. Yeah, I'm Kashish.
Hello.
Yeah. I was just wondering the volume that we are calculating is
Yep.
going to be the volume of whole entire anchor.
The volume you're calculating will be the volume of the iron in the anchor.
So
This,
of the whole entire, right?
well,
Not just.
because the buoyancy, right, that we're calculating is 200 when it's completely submerged. So because it's completely submerged, the displacement is the same as the volume of the anchor.
Okay. Okay. Thank you.
So this V here, the displacement V is the same as the volume V of the anchor.
Okay. Thank you.
You're welcome. Okay, so hopefully everyone's got 3 done. I will say that 5 is very tricky. Oh, sure, Julie. So there were 2 steps. Part A, you were asked to find the volume. So we just used the Archimedes equation for that. And then part B, you were asked for the weight of the anchor. So first we found its mass, and then we just multiplied by G to get the weight. Now, when I put up things like this, I do encourage you to, you know, if you didn't get it on your own, to like cover up the solution and then try and do it again later, so that you can, do it with understanding. Practice these questions until you can write them out quickly and with complete understanding. And so try and work through these problems. With the exception of number 5, you should be fine, I think. And do them until you can do them, easily and with understanding. Now, I sent out a post from our Moodle page. I don't know if it's gone out yet. They seem to be delayed a lot this year. But it's about the office hour system. And so in the post, there's a link. And so you just go to this link. And when you get there, you see something like this. And it would be, not just for this week. So this is the current week, but it will be for following weeks as well. And so I think I've got it set up right so that these correspond to times after our class. You don't see Monday times just because you have to book more than 24 hours ahead, or more than 8 hours ahead or something like that. So, and all you gotta do is you just click one of these green bubbles if you want to book that time. And then you're booked, and then I'll just send you a Zoom link, and then just meet by Zoom to talk about things. So this is the office hour appointment system. No, that's not a live link. Okay, and so the live link will appear in a Moodle post that should go to your inbox shortly. And so you can book times. It's just that simple. Just click on the button, and you have to fill in your name and the thing you want to talk about. And I think I restrict it to 1 appointment per day per student, just so that it gets spread around a little bit. Anyway, I've used this for a number of years and it works really well. So that takes care of office hours. And so now I promised you one more example for today, and we're going to turn back to page 39, please, and do the iceberg example. Now, first of all, up at the top of page 39, we drew a conclusion. Basically, we used the theory of buoyancy to show that an object more dense than water would sink, an object less dense than water would float. And then there's an example of that, and I just have a slide here for you. So here's a real Coke, and then these are just two pictures, and you can see they're filled up with water. Real Coke sinks, Diet Coke floats. The cans are the same size, and so the difference between them, well, the real Coke is more dense, the can of real Coke, and that includes the Coke liquid, the aluminum can, and then there's obviously some carbon dioxide up at the top from the carbonation. So that composite object, this is more dense than water, and the Diet Coke is less dense than water. Why is that, do you think? Can you hear me? Somebody type something, please. Indeed, it's the sugar. It only takes a little pinch of aspartame to create a sweetness impression in the Diet Coke, because aspartame, yeah, for whatever reason, it's very active in our sensory system, I guess. And so you just need a little pinch of aspartame, but of course the real Coke has got like 10 teaspoons of sugar in it, so that increases its density. So that's why real Coke will sink, but Diet Coke will float. So underneath that, page 39, this is the example we'll finish up with. It's the iceberg. Now you've heard that you only see 10% of the iceberg and there's 90% below, and we want to try and prove that. So let's do this together. Okay. So first off, Diet Coke floats and real Coke sinks. All right, so now our example. So we've got an iceberg, it's floating, so that means the weight and the buoyant force, those are the only two forces acting on it, they have to be balanced. All right, so we continue with our analysis. Now, the buoyant force, well, we know that's rho GV. So which rho? Well, it's the density of the displaced fluid, which is going to be seawater. And which V? Well, it's going to be the volume submerged or displaced. Now, the iceberg is not totally submerged. How much is it? How much of it is submerged? Well, that's what we're trying to show. So we're going to introduce a variable. So let's let, sorry, I just got ahead of myself there. We'll make an assignment. Let's let F be the fraction above. Okay, and so that might be, well, we're trying to show that that's 0.1 or 1/10. If F is the fraction above, then 1 minus F is below. And that would be, so we're hoping that this is 0.1 and this is 0.9. So that means the submerged volume is 1 minus F. It's that fraction of the total volume V. So that's an expression for the amount that is submerged. So there's FV above and 1 minus FV below. So there's an expression for the buoyant force on the iceberg. Okay, well, The mass is going to be the density of ice. Maybe I'll do it here, just so I have a little bit more room. Otherwise, I'm going to be crowded down below. So this is going to be, the mass will be the density of the ice times the volume, and then obviously you multiply by G. So the mass is the density times the volume. So we've got this equation for the floating iceberg. Now, this is good because V and G both cancel, and we know the two densities, so we should be able to solve for this fraction F, which was the thing we were looking for. So substituting in the given densities, we do indeed get 10% of the iceberg is the fraction above. So hopefully you've all got that down now. Yeah, and so in this example, we use the equations that we started with, back in example 5 and example 6. So this equation was just force balance. Then we used the Archimedes equation to get an expression for buoyancy. And we had to pay attention to, what's the displaced fluid and what's the displacement. Use the correct rho and the correct V. And then finally, we just used the object density equation to replace mass with density times volume. So really, all of the problems that we've done today have used a combination of those three equations. So hopefully you're, gaining some proficiency and confidence with this theory. And at the end of today, we should know where buoyancy comes from. It's the fact that pressure increases with depth. So there's a little bit more pressure force on the bottom than there is on the top. It's directed upwards. And we know how to calculate buoyancy. It's rho GV. And then we know how to solve problems related to buoyancy using either force balance from physics 11, the density definition from science 9, or this new Archimedes equation. So work on those 5 examples, plus the 5 from last time. I mean, you always kind of go back and keep working on things to master it. We are still doing fluids. Next class will be on fluid dynamics. And there's a pre-lecture video for it. And our format will be pretty much the same. There may be time next class for a quiz on buoyancy. So make sure you do get these 5 questions done. And if you have anything you want to ask, you now know how to book an office hour appointment through that You Can Book Me link. So this concludes our presentation for today. I hope this class is going okay for you and that you're not having any technological issues. I think Zoom is a much better platform than Big Blue Button, so I'm probably going to keep using it as long as we can. I hope it's okay with you guys. Do let me know if, how it's going. Is the tech okay for you? Can you hear me? Am I going too fast? It's difficult when I'm just speaking to a computer screen because, with pacing, I kind of look at you guys and, if you're still looking down at the page and writing, I wait. If you look up, then I say, okay, I can go on. Well, I don't get those cues in this sort of format. So do give me some feedback. Yeah, I guess I'll be talking to you real soon. That's a good question, Matthew. I've actually been recording this one. So yes, this one will be on the site. I don't know. Yeah, honestly, I don't want to just record them all because I think there should be some incentive to actually attend and participate. But certainly the first few I'm going to record. Okay. So I have been recording it. Zoom lets me do that. And there's one student in particular who communicating with me ahead of time saying, look, I can't make it, will it be recorded? So I did that for this class. So there you are. Okay, so have a great day. Do communicate with me because I'd like to know how you're doing. And I can't get that information from my computer screen unless you text me or something like that, or message. Take care, all.